Welcome to the lecture series of Discrete Mathematics. Today we are going to discuss a new terminology, tautology. Look at the definition of tautology. A statement formula which is true always irrespective of the truth values of the individual variables is called a tautology. Example, P or negation P is a tautology. When we can say that a statement is a tautology. If the final value in the truth table column, if it is true, the truth value is true, then we can say that it is a tautology. Here is an example is given, P or negation P is a tautology. We know the truth table for P or negation P. So it takes the value true. When P is true, then obviously negation P is false, isn't it? If P is false, the negation P is true. So P or negation P or negation P is true or true, final value is true. Here false or true, the value is true. Look at this column, the last column. The last column value is true only. So this is the reason why this P or negation P is called it as tautology. Okay. Then the next definition is contradiction. A statement formula which is always false is called a contradiction or absurdity. Okay. So when we can say that a statement is a contradiction, if the final answer in the truth table, if the final value is a false value, then we can say that that is a statement is a contradiction. Example, we can take P and negation P. Here we have taken P or negation P. Same manner, if we go with the P and negation P, we can get the final value is false, so that we can say that it is a contradiction. Then the next one is a contingency. When we can say that a statement formula is a contingency, it should be neither tautology nor contradiction is called a contingency. It means what? That is true or false. Both value can be in the truth table. Then we can say that the statement is a contingency. Example, P biconditional Q is a contingency. That means we can get the truth value true as well as false. Then we can say that it is a contingency. Then the next important definition under this topic is equivalence. Equivalence, when we can say that two statement formulas are equivalent. Two statement formulas A and B are equivalent if and only if A biconditional B or A biconditional, that is a two-sided arrow mark, we can say that it is a biconditional, is a tautology. It is denoted by the symbol A equivalence B, which is read as A equivalent to B. So hereafter, if you are seeing like this symbol A equivalent to B or P equivalent to Q, means we can read it as equivalent to. So A is equivalent to B. When we can say that A is equivalent to B, if and only if. When? If and only if A and B are equivalent, if and only if A biconditional B is a tautology. It's a definition for equivalence. There is a note, that is important remark under this topic. The remark is, to prove two statement formulas A and B are equivalent, we can use any one of the following method. So what are the methods? The first method is using truth table. We show that truth values of both statement formulas A and B are same for each 2 power n combination. And the method 2 is assume A by applying various equivalence rules, try to derive B and vice versa. And the method 3 is A biconditional B is a tautology. So what is the remark says? The remark says that when we can say that two statement formulas are equivalent to each other, when we can say like that means first either we can prove by truth table value, if it is true or false, according to that we can say that it is a tautology, and or otherwise by applying various rules, equivalence rules, we can apply the equivalence rules, so that either if you are assume A to bring the B, or if you assume B to bring our A, like that also we can proceed by applying the rules. Or the third method is the biconditional, that is A biconditional B is a tautology, if you prove this also. So there are three methods. Sometimes in the question paper itself the method will be mentioned. According to the method we can prove that given given propositions are equivalent or not. Okay, so before we are doing the problem, we can have some formulas, that is the laws under the discrete mathematics. All the laws we know very well, that associative law, distributive law, this thing and all we have studied in the 9th 10th itself under the set theory. Instead of the set theory notation, here we are having the statement notation, that's all. That is the difference, P, Q, R, like that the statements are given, compound statements. For that we are applying the distributive rule, associative rule, or De Morgan's law, all that things we are applying. In our book, prescribed book, we have all the laws in a single page. You just go through all the laws. There is nothing to remember or nothing to memorize is there. Just to try to understand all the laws, where we can apply the law, how to apply the law, that's it, so that we can do the problems. Okay, so now directly we are entering into the problem. While we are doing the problem itself, you can understand the laws, how we are applying the laws. Look at this question. Show that negation P and negation Q and R, or Q and R, or P and R equivalent to R. So this is the way the question will be there. So in this question, it's directly given that show that. So it's not mentioned we are supposed to use truth table or reasons, nothing is given. It's given that show that. Okay, so how we are going to prove this one? Just we are taking the left hand side and we are going to bring the right hand side R. So in this way we have to do the problem. First we will take the left hand side, and here we are supposed to give the reasons. What are the law we are applying here? That thing we are supposed to write. It's very compulsory. So that only we can get the full mark. So in this question we have considered that a negation P and a negation Q and R. Okay, and the next one R, Q and R, or P and R, it's given. So how we are going to prove this one? So in the left hand side we have taken as it is, negation P and A, negation Q and R, or Q and R, or P and R. Now keep the first term as it is. Look at the last two terms. In this one we have and R is commonly, that is Q and R. Here also P and R. So how we are going to write this one? We have to put the symbol implies or equivalence. Okay, so keep the first term as it is. So negation P and negation Q and R, keep this one as it is. Or only in the second term we are taking the and R outside. So what is the remaining? Q is there, or P is there. So we can write this as Q or P and R. Okay, Q or P and R. So we have distributed this and R. So if there is two connectives are there, we have to apply the distributive law. In this way we have to remember, two connectives are there, R is there and is also there. If it is the case, we have to apply the distributive law. So here the reason we have to write distributive law. Simultaneously we have to give the reason. Now look at this one. In this one also we have, look at this, negation P and negation Q and R. So in the first term, look at here also and here is also and, same operator is there. So in this case same operator is there, we can apply the associative law. So this can be written as negation P and negation Q, okay, and R. Okay, in the first term we can take the negation P and negation Q and R. Okay, or now the next term Q or P, second term as it is Q or P and R, we keep the second term as it is. So here we have applied the associative law. When we can apply the associative law? If two symbols, that is, look at this, here is also and, here is also and, same operator is there, we can apply the associative law. Okay. Now look at these two. In these two also, negation P and negation Q and R. Here R, Q or P and R is there. So in this case also, look at this one. Here is also in the first term again we are having and R, and here is also and R. So we can write this one as negation P and negation Q or Q or P. So in this term Q or P, okay, for these two we can write and R common. Okay, so again we have used distributive law. When we can apply the distributive law? Two logical operators, that is here it is or is also there, and is also there. In this case we can apply the distributive law. Now look at the next one. Here in these two terms we have negation P and negation Q. Whenever we are having the negation, we are supposed to remember the De Morgan's law. So here you can take the negation outside. So this will become as P or Q. Okay, or here it is Q or P and R. So here we have applied De Morgan's law. Okay. So when you are applying the De Morgan's law, you can verify that when you are applying the negation inside the bracket, again we are getting the same term, that is negation P, negation of R is and negation Q. Okay, so that is the way we can recheck your answer. And now here you look at that Q or P is there. This can be written as P or Q. So which implies negation P or Q or P or Q. Okay, and then and R is common. So Q or P can be written as P or Q. What is that law? That is commutative law. Okay, so that is commutative law. Now look at this one. This is of the form negation P or P. Okay, here also P or Q. You consider this one as a P and this is also P. So this is of the form negation P or P. So negation P or P equivalent to true. Okay, so this whole value will become as true and R. Okay, we know very well that and means multiplication. So P and T, the value is always any proposition with the T. The value is what? Same proposition. So here also T and R means T is 1. Okay, 1 into anything, same number will come. So which is equivalent to R. So now look at the question. We have taken the left hand side and now we have arrived the right hand side answer. So which is equivalent to R. Okay, therefore we have arrived the result, hence proved. Question is only show that or hence showed. Okay, so like this way only we have to give the reasons in the nearby of the problems. Okay, so this is the way we have to do the problem under the reasons. Look at the next question. Prove that P or Q and negation of negation P and negation Q or negation R, or negation P and negation Q or negation P and negation R is a tautology. So we are going to prove this by reasons only, not truth table, but in the question paper itself it will be mentioned without using truth table, prove this a tautology. In that case we have to do by this method only. If it is given truth table means we are going for truth table also. So how we are going to proceed this one? First we are going to take the second term. Okay, the second term only first we are going to take and then the last one term. So after find out these two terms values, again back to this equation we will get the answer. Like that we are going to prove. What is the answer should be? Answer should be true. Then only we can say that given statement is a tautology. So how we are going to proceed means first we are going to consider this term only. So look at the proof. Consider, take this one, negation of negation P and negation Q or negation R. Here it is small q and small r. I have written capital Q and capital R. Doesn't mean you can write this small q and small r. Okay. Okay. So negation, as I told you already that whenever you are seeing negation in this case, you have to remember the De Morgan's law. Okay. So here also we are going to apply the De Morgan's law. So what will happen when you are applying the De Morgan's law? Okay, negation of negation P and this one if you are taking the negation outside, what will happen? Which will become as negation of Q and R. Okay, since De Morgan's law. First we have applied the inside the bracket, the De Morgan's law we have applied, so that we got Q and R. Now again applying this negation inside this bracket, negation of negation P is P. So which implies P, negation of and is R, okay, and then negation of this whole term, negation of negation Q and R. Here also we are applying the De Morgan's law. Okay, negation of negation P is P. So by the case this will become as Q and R. Okay, so Q and R. So P, R, Q and R. So again this can be written as P, R, Q and P, R, R. Okay, what is the law? Here we have applied it. Look at this, R is there and is also there, and we have written P, R, Q and P, R, R. What is that law? That law is distributive law. Okay, so now the second term become as P, R, Q and P, R, R. So we can take it as equation 1. Okay, now we will consider the last case, that is the last term. Consider negation P and negation Q, or negation P and negation R. Okay, consider the last term in the question. So here also we have negation only. So this can be written as, in the first term, if we are taking the negation outside, this can be written as P, R, Q. Okay, R, and here if you are taking the negation outside, negation of P, R, R, since De Morgan's law. Okay, so since De Morgan's law. Now you look this, here negation of P, R, Q or negation of P, R, R. So here also we can take the negation outside. So what will happen? Negation of P, R, Q and P, R, R. Okay, so this is the way we can write. Here also we have applied the same De Morgan's law. Okay, in both the term we have taken the negation outside. Now this is our equation 2. Now back to the given equation, substituting these two values in the given equation. From equations 1 and 2, look at the given equation. Given equation is P, R, Q and we are supposed to write this one. Instead of the second term, we are going to write the equation 1. What is that? P, R, Q and P, R, R. Okay, so instead of the second term we have written this, and the second equation, from the second equation, instead of the last term, from the second equation, this can be written as negation of P, R, Q and P, R, R. Okay, so from the equations 1 and 2, now we have arrived the given equation in this form. Okay, P, R, Q and P, R, R, or negation of P, R, Q and P, R, R. So in this one, P, R, Q and P, R, Q, P and P is equivalent to P. Okay, P and P is equivalent to P. So by applying that, instead of this first term, we can write it as P and Q. Okay, so P, R, Q and P, R, Q. This is of the form P and P. So this can be written as P, that is P, R, Q. Okay, and P, R, R. Okay, write the remaining as it is, or negation of P, R, Q and P, R, R. Okay, this second term as it is we have written, only here we have applied that P and P equivalent to P. So in that one, that is called it as idempotent law. Okay, so now look at this one, P, R, Q and P, R, R, P, R, Q and P, R, R, or negation P of Q and P of R. Look at the same term. Okay, P, R, negation P. Okay, this is of the form P, R, negation P. You have to treat the whole term as a P. If you consider this whole term as P and this is a negation P. Okay, so this is of the form P, R, negation P. P, R, negation P equivalent to what? Equivalent to true. Okay, so P, R, negation P equivalent to true. So instead of this we can write it as implies true. So our final answer is true. Therefore the given statement is a tautology. Okay, so we can take the second term separately, applied the rules, and again the last term separately, applied the rules. We got some proposition, and back to the given statement, applying that we got the final answer as true. If final answer is true, then the given statement is a tautology. Look at the next question. Show that P conditional, Q conditional or conditional, P conditional Q conditional, P conditional or is a tautology. So this is a question. Here also we are going to apply like the same manner in the previous result. Look at the solution. We will take the given statement as it is. Okay, P conditional Q conditional R this is the first one, it's given. Conditional P conditional Q conditional P conditional R. Okay, this is what given in the question. So now what we are going to do is we are going to apply this P conditional Q conditional P conditional R. So which implies, okay, this can be written as P conditional Q conditional P conditional R. Okay, here we have applied that result. This term as it is P conditional Q conditional P conditional R. So here we have applied P conditional Q conditional R can be written as P conditional Q conditional P conditional R. That is what we have applied here. Okay, so the next one is P conditional Q. We have a result P conditional Q which is equivalent to negation P R Q. Okay, it's a equivalent relation. So using that result, this is of the form, this whole thing you can consider as P and the whole thing you can consider as Q. So this is of the form P conditional Q. Okay, so in that case we can apply the result, that is P conditional Q can be written as negation P R Q. So in the first term we can apply the negation of P conditional Q conditional P conditional R. Okay, negation P, okay, negation P R Q. Okay, so in this second term we can apply the R. Q is P conditional Q conditional P conditional R. So we have applied this result. So now this is of the form negation P R P. Okay, so look at the term. So here this is of the form negation P R P. So what is the result? Negation P R P. We know that negation P R P is equivalent to true. Okay, so this is of the form negation P R P. So which is equivalent to true. So the final result we arrived as truth value T. Therefore given statement is a tautology. Therefore given statement is a tautology. Using truth table means we can go with the truth table. Here it is not mentioned, so that we have arrived like this. So here we have applied the reasons, all that things we have to look at the book and remember all the result, associative law, the distributive law, De Morgan's law, idempotent law, all that laws we have to understand from the book. By applying the result we can get the actual value of the given statement formula. So the statement formula is true, we can say that given statement is a tautology. If it is false means we can say that it is a contradiction. Okay, thank you for watching.